Let's start looking at particles and waves, and this time the Compton effect. Let's start with a little bit of background. In his photoelectric effect, Einstein explained how light is composed of packets of energy called photons, and the experiment was basically light of sufficiently high frequency striking a metal releases electrons from that metal. So let's look at some of the properties of photons. Starting with relativity, E equals mc squared divided by square root of 1 minus v squared over c squared. So this is the total energy of a particle. And then rearranging this equation, so I'm multiplying both sides by 1 minus v squared over c squared, by the square root of that. And if we remember that the photon travels at the speed of light, then the v here would just be c. And then we end up with E times 0 equals mc squared, because v squared over c squared is c squared over c squared, which is 1. But then 0 is mc squared. And since we know that the speed of light is 3 times 10 to the 8th meters per second, then the only way mc squared can be equal to 0 is if the mass of the photon is 0. So here is one conclusion that we draw from relativity. Now also, since the mass of the photon is 0, then we can't really use the energy and momentum that we used to be able to use before, so we have to come up with different expressions for them. So back to E equals mc squared divided by square root 1 minus v squared over c squared, and then the momentum of a particle was m of v divided by square root of 1 minus v squared over c squared. So from these two expressions, we can draw the conclusion that momentum of a particle can be written as ev over c squared. In the case of the photon, again, v is the speed of light c, so momentum of a photon then is ec over c squared, which means that it's just e over c. So we'll see that we'll have to use this expression for momentum quite a bit. Now remember that the photon energy was given by hf, so we can rewrite this as hf divided by c. So we can rewrite this as h, and f is c over lambda divided by c. Now we can cancel out the c and end up with h over lambda as another expression of the momentum, only in terms of the wavelength of the particle. Now another physicist by the name of Arthur Compton scattered X-rays, which are high-energy photons, off of electrons in graphite. So here is the experiment where an incident photon strikes an electron in the graphite, and the electron is going to scatter in this direction, and the photon is going to scatter in a different direction. And we'll call this the incident photon, this the scattered photon, and this the recoil electron. I guess I should write that on here. So this is incident photon, this is the recoil electron, and this is a scattered photon. So the remarkable thing about this is that Compton measured the wavelength of the scattered photon and noticed that it is longer than the wavelength of the incident photon. So lambda prime was larger than lambda. But remember that there is an inverse proportionality between wavelength and frequency, so this means that the frequency of the scattered photon was less than the frequency of the incident photon. And also remember that energy of the photon is h times f, which means that there was energy lost in this scattering. So the scattered photon had less energy than the incident photon. So it's a classic problem of collisions. We would use both conservation of momentum and also conservation of energy. So if we write those out, we have the energy of the incident photon has to be equal to the incident of the scattered photon plus the energy of the recoil electron. And for momentum conservation, momentum is a vector, so I'm going to have to write it as initial momentum of the incident photon is equal to momentum of the scattered photon plus momentum of the electron. And in the case of momentum, we would have to go and solve this in the x direction and also in the y direction. So we'll pick up some cosine and sine terms in here. And the derivation is quite complicated. You have a lot of algebra to do. So I'm going to skip that bit and just say that the observation that Compton made was that the change in wavelength between the incident and the scattered photon was h over mc times 1 minus cosine theta. So this is the equation that he obtained. And this h over mc is called the Compton wavelength of an electron, because when the X-rays struck the graphite, the electron was the particle that was scattered. So if we plug in the Planck constant here and the mass of the electron and the speed of light, we end up with 2.43 times 10 to the negative 12th meters. So that would give us the Compton wavelength of the electron. So here we have a little summary of equations. Here's the equation that Compton came up with for the difference in wavelengths of the scattered photon and the incident photon as a function of the Compton wavelength of the electron.